Hello everyone and welcome to the 24th lecture of the course Advanced Structural Analysis. We have seen the last session in which we discussed a problem based upon the simple flexibility as well as the generalized flexibility cases. And now with this session we will try to extend the same problem to the stiffness approach. This is the concept which we will cover in this session, that a problem with the simple and the generalized stiffness approach we will consider, and the problem is same, which is having a partial restraint condition. As a part of the problem statement, we have a system which is subjected to uniformly distributed load as well as a concentrated load in the given system, and one of the end or one of the support is provided with the spring measure, which is having a identified value of the flexibility. One can also inverse it and get the value of the stiffness for the given system, which could be defined as 3 EI upon L cube for the given problem. Now, as a given problem, we want to solve using the simple stiffness approach. First, we look into the steps which we typically do. The simple or the direct stiffness approach typically looks for the choice of the unknown set of deformations in the system, and to define those, first we convert the given system into a kinematically determinate system. A kinematically determinate system is having a unique choice. So, that is one of the advantage which comes out with the stiffness approach, that rather than going with a system where the choice of the redundant is dependent upon the user, the stiffness based approaches always come up with a kinematically determinate system which remains a unique system, and that also becomes more suitable when we extend the given methods to the computer programming. Now, as a standard method, the different steps have been defined. We identified the degree of kinematic indeterminacy for the given problem. Then we restrained all the degrees of freedom, and that becomes our kinematically determinate system of the given problem. Further, we break down the given system into two parts. A system which is kinematically determinate, that means all the degrees of freedom are restrained, is subjected to the external load, and we evaluate the reactions corresponding to these fixed ended components of the given system. And then we also one by one release individual degrees of freedom which are available to take place in the original system, and consider those as an additional system to the originally defined kinematically determinate system. The addition of all these systems together becomes the net statically similar system which we have generated in the given problem. And to enforce this condition of the statically similarity, we identify the conditions of the equilibrium in the given system. So, the equilibrium of the forces with respect to individual degrees of freedom which are free in the given problem is identified, and that gives us the necessary condition to evaluate the unknown set of deformations. Then further we do the simple post processing to calculate the member forces and the support reactions in the given problem. Now, we will just see that the next step of the given analysis. As a first part, we evaluate the degree of kinematic indeterminacy of the given system. We will just see the system to identify the kinematic indeterminacy, and then as a next step 2, we restrained all the degrees of freedom to make the system as a kinematically determinate system. So, if this is the problem originally given to us, we realize that at the joint A we have 1 degree of freedom which is restrained and 1 degree of freedom which is free. At the joint B also we have 1 degree of freedom which is free. At the joint C we have 1 degree of freedom which is free, which is the rotation, as well as the vertical translation is partially free at the given system. So, we consider total 4 degrees of freedom which are available in the given problem. One must note that at the given problems we are considering that any point can have possibilities of a vertical translation or a rotation in the given system. As it is a beam member, we are not considering right now the axial deformations or any other 3D effects in the given problem possible. So, the simple consideration of the vertical translation and the rotation about the normal axis or the normal plane of the given system are considered, and with respect to that we identify theta A, theta B, theta C and delta deformation at the point C are the 4 number of available degrees of freedom in the given problem. If you want to convert now it into a static kinematically determinate system, the procedure is simple. We consider a system which is fully restrained for all the degrees of freedom, and in this manner we eventually identify a system like this, in which we have all these degrees of freedom now fully restrained. The system cannot move at any of the points, and now this is subjected to the external load which has been defined in the original problem. We consider that this is one part of the system which is not same. So, along with that we also release the individual degrees of freedom one by one. So, theta A, theta B, theta C and delta C one by one are released, and that substitution on top of this given system will give us the same original problem which we want to solve. Now, to see this part in the next steps, we can check here that the step 3 we break down the system into a kinematically determinate system. So, as we did, this is a kinematically determinate system which is now having a degree of kinematic indeterminacy 0, because now there is none of the degrees of freedom which are available in the given problem. With respect to the identified member forces, we have calculated the support reactions or the fixed ended reactions of the given system. This has been obtained with respect to the standard formulas which we have discussed earlier in the force method. In any of the reference texts, we can evaluate these values, and also it can be evaluated generally by the standard force or displacement method for the given system. Once we have calculated all these values, we identified that this is the response due to the external load on the kinematically determinate system. So, we identify this as a P of L component of the given system, and P of L at this point with respect to the given conditions of the system will become that we have the corresponding values which are in the direction of the degree of freedom 1, the degree of freedom 1 which is corresponding to the theta A, degree of freedom B which is corresponding to the theta B, the component of the rotation at the point C which is theta C, and the vertical translation in the given problem which is delta C of the given problem. So, we can identify the set of forces, the fixed ended forces of the given system with respect to the individual directions of these 4 degrees of freedom, which are theta A, theta B, theta C and delta C of the given problem. We realize that these values appear as W L square upon 12, the value which is corresponding to the first point. It is considered to be positive because we have evaluated that the reaction response is in the anti-clockwise manner, which is positive as per our sign convention. Theta B has been evaluated with the minus of W L square upon 12 response, which is opposite to the evaluated or the identified positive sign convention of the given system. Theta C, which is defined over here, is not contributed by any of the joint loads. So, this is 0 for the given problem, and delta C, which is corresponding to the given point C in the translation direction, is having a contribution of the load W L. So, it is defined by minus of W L because the positive direction is considered to be upward. In the same manner, now we also release individually one by one all the degrees of freedom in the given problem. So, as we have considered theta A, theta B, theta C and delta C, we release individually all these 4 degrees of freedom in the given problem, and corresponding to these 4 degrees of freedom which have been released in the given problem, given system, we evaluate the end forces of the given problem. And with respect to say the theta A, which is considered to be of 1 unit, we evaluate that the end moment which is generated over here is 4 EI upon L, theta upon L, as the theta value is 1 unit. So, it becomes 4 EI upon L in the given system. Similarly, the far end moment of the given system is 2 EI upon L. The set of reactions can also be obtained for the given system. In the same manner, we extend the rotation at the point B, which is theta B. This will generate the set of forces in both the member AB as well as the member BC of the given system. Similarly, we can evaluate the rotation at the support C. Again, this will generate the member forces at the end of the joint B and C of the given problem. And finally, we add the translation in the direction of the joint C, which will give us the unit deformation in the direction of the given point C, and that will also generate the set of forces. More importantly, when we add the component of the delta C at this given problem, we realize that this is not a regular fixed ended beam, but rather it is also supported by a spring system at the bottom. So, any of the changes which are taking place in the translation direction of delta C will also require a work to be done against the reaction of the given system. That is why the regular reaction force which we typically generate in these systems, which is 12 EI upon L cube, will also be supplemented by the contribution of the stiffness of the given spring member. So, that has been added with the additional spring stiffness, because at the given point it is not a simple system which is subjected to a translation in the vertical direction and which will be having the amount of the force over here as 12 EI upon L cube in the given problem, but as it is also supported by a spring member, any of the work which is done with respect to a unit deformation in the direction of delta will also require us to work against the spring stiffness, and that is why the spring stiffness has also been added with the given system. So, one must understand that while we are considering the system to be made up of the given support C, which is shown as the fully restrained, but while writing the stiffness contribution, we have added the parameter which is including the contribution of the spring stiffness in the given problem. Once we have added this part, we consider that the individual coefficients which have been obtained over here in the direction of theta A, theta B, theta C and delta C will contribute to the stiffness of the overall system. So, I can write that the stiffness coefficient with respect to the first parameter, which is say theta 1, theta at A being 1 unit, will give me the force in the direction of theta A itself, and that force will be becoming the first coefficient or the coefficient of S11, and that is 4 EI upon L in the given problem. In the same manner, corresponding to same theta A equal to 1 unit, the force which is obtained in the direction of theta B is calculated, that is 2 EI upon L, and that becomes the second component of the stiffness coefficient in the given system. So, this manner we can keep on contributing all the members by looking at these specific forces which have been identified, and this gives us the overall stiffness matrix of the given system, and we describe that matrix in the standard form which appears like this. So, we have shown here with the symbol K in the given problem, which typically means that the stiffness of the given system with respect to all those components has been identified. 4 EI upon L with respect to the component over here, which is with respect to the given theta A equal to 1 unit. Similarly, 2 EI upon L, which is corresponding to the second degree of freedom direction. Then corresponding to the third degree of freedom direction, the forces are 0, and same with the fourth. So, these are the component which are with respect to theta A equal to 1 unit. In the same manner, one can also go with the theta B equal to 1 unit and again identify all the 4 coefficients of the given stiffness matrix, and that will also be appearing similarly as we have identified in this figure of the given system. And once we do this for all the 4 degrees of freedom, we generate the overall stiffness matrix of the given system, which is a 4 cross 4 matrix for the given problem. The P of L component, which has been already defined for the problem, has been also identified. In the same manner, we have also considered that P of L, the manner we considered earlier with the component of the WL component in the previous case. So, over here we have considered that the delta C contribution, which is considered with respect to any of the member forces with respect to which the fixed ended reactions will be obtained. So, WL square upon 12 and WL square upon 12 with the negative sign has been identified, but with the direction of the component at the joint C, we have considered theta C component being 0, whereas delta C was considered to be of the amount WL, which was with respect to this given load. But we will do that, we will modify this component as it is active at the joint of the given system. So, we will not be considering this as a part of the member force contribution. So, this contribution of the given system will be considered as 0 itself, whereas this part will directly go to the contribution of the equilibrium condition of the given system. So, with this point in mind, what we do, we consider over here that the respective forces of the P of L becomes WL square upon 12, and the second force is also minus WL square upon 12, whereas the component of the equilibrium of the given system will require us to identify the given force, which is of amount W minus of WL as it is in the downward direction. And with this point in mind, now we have identified the load vector of the given system, which is P, which is identifying the equilibrium condition, the external load component of the given system, which is due to the fixed ended reactions of the given system. These are the unknown set of deformations which we want to evaluate in the given problem, and we have also evaluated the stiffness coefficient of the given problem. So, now we can identify the standard equation of the system equilibrium, and we can consider that the unknown value of the delta can be evaluated by solving the values of the given system. So, once we evaluate the response of the given system, one can get the value of delta in the given problem. By doing the simple inverse of the stiffness matrix, one can evaluate, and these are the values which have been identified. So, this is the value of theta B, this is the value of theta C in the given problem, this is the value of theta A, this is the value of theta B in the given problem, this is the amount of the rotation at the point C, and this is the translational displacement at the point C of the given problem. The sign has been accordingly defined with respect to the positive convention which we have taken. So, for the original problem, we have considered that at the joint A, the rotation is considered to be anti-clockwise. At the joint B, also the rotation is considered to be anti-clockwise positive. At the joint C, also the rotation is considered to be anti-clockwise positive, and the translation is also considered upward positive. So, if the value comes out here as a positive, that means the rotation at the joint A is anti-clockwise itself. At the joint B, it is clockwise, at the joint C also it is clockwise, whereas at the joint C the translation is in the downward direction. With these values in mind, now we can evaluate the post processing of the given system. So, in order to do the post processing, we come up with the given system that can be generated with respect to all the unknown parameters which we need to evaluate as a post processing step. We have 4 member forces which are corresponding to the 2 beam member ends AM1 to AM4 in the given system, and at the same time we have also one member force in the spring coefficient, that is the AM5 in the given problem. So, as a first part of the evaluation, we want to evaluate the values of AM1 to AM5 in the given system. The second part of the evaluation also requires us to calculate the reaction forces which are R of A, R of B, and also we are evaluating the reactions at the support C of the given problem, because this will also be one of the redundant or one of the unknown parameter of the given system. So, this also will be evaluated for the given system. Of course, later we will try to identify that this RC value, the amount of reaction which is effectively appearing over here, is same as the amount of the member force which is appearing as a AM5 in the given system. Now, in order to evaluate the values of these given systems, we can utilize the similar concept which we did earlier for identifying the given system. We evaluate the individual deformations of the given system one by one, and corresponding to those individual deformations, we calculate the amount of the member forces or the amount of the support reactions in the given problem. What we mean to say is that as we are including in the given problem, as this is the originally defined problem of the given system, considering that the system initially is fully restrained, we have considered a system like this, and now one by one we release all the delta or the degrees of freedom of the given system, which includes theta at the point A, theta at the point B, theta at the point C, and delta at the point C of the given problem. So, once we release theta at the point A, corresponding to that we can evaluate that what are the system forces which are appearing at these 2 points of the given system, and they will become the values of R of A and R of B contributions with respect to theta A of the given system. In the same manner, one can come ahead with the second parameter where the rotation at theta B will be evaluated, and corresponding to that theta B rotation, again we will evaluate these system reactions, and they will become the rotation, the system reaction at the point A and the point B with respect to the rotation of theta B in the given system. Similarly, we can do this for the remaining other 2 degrees of freedom also of the given problem. In the same manner, one can also evaluate the internal member forces of the given system, and that will be included by a standard matrix which is called as AMD, which is the corresponding member forces with respect to the unit deformations applied in the direction of theta A, theta B, theta C and delta C of the given system, or A of RD, which are the system reactions appearing with respect to all these degrees of freedom of unit margin in the given problem. Now, in order to do so, we can easily contribute the given problem. We can go ahead with the similar calculation and consider it that a simple problem which is considered with respect to the external load, which will be evaluated, will have these values of the given system. So, we can consider that for the given system where the individual forces are applied for the unit amount of rotation over here, say theta A equal to 1 unit. So, we get the value of the reaction at this point, which is 6 E I upon L square. We get the reaction at the point B, which is 6 E I upon L square in the downward direction, and we get the reaction over here which is of the 0 value. So, corresponding to the theta A as a component in the given problem, we get the value of the A of R in the given system of the reaction at the point A is 6 E I upon L square, which is positive. At the point B, it is minus of 6 E I upon L square, which is negative, and at the point C, it is 0, which is not having any contribution of the reaction due to the rotation at the point A in the given system. In the same manner, we go with the second system where we apply the rotation at the point B, theta B equal to 1 unit in the given problem. Again, we evaluate the set of forces in the direction of R of A, R of B and R of C in the given problem, and these values have again been identified corresponding to their net resultant of the given system, and these values typically constitute the overall component of the matrix A of RD in the given system. In the similar manner, one can also evaluate the response of the system with respect to the internal member forces. As we are applying the unit forces in the given unit deformations in the given problem, we are also generating these support reactions, and with respect to those, the internal member forces can also be identified. So, when we applied theta A in the given problem, we realize that in the direction of AM1 and AM2, we will be generating a force which is of the same margin as the set of reactions are appearing at the ends. One can just correlate this by saying that if this is the member where this is R1 and this is R2 as two values of the end support reactions, by making a cut over here, if we just make the system into two parts. So, this R1 and R2 will be fully balanced by the component over here which is R1 and this opposite moment of R2. So, this is a cut which is made very close to the given end point. So, now in the second remaining component, the forces which will be translated will be in the same sign as the reactions of the given system were initially identified. So, in order to calculate the member forces, one can directly look at the directions of the support reactions and identify the same directions for the given member force component as well. So, with this idea in mind, I can go ahead with the calculation of the AM1, which is minus of 6 EI upon L square, which has been identified here, AM2 which is 2 EI upon L with the positive direction, AM3 and AM4 which are corresponding to the member 2 have been identified to be 0 because this member is not subjected to any component of the support reactions of the given system. And as this member is not subjected to any support reaction, the spring force AM5 will also be 0. And with this point, we have identified these 4 values of the given system. So, right now we are only showing the 4 values, the spring force component has not been shown over here and we will be calculating that separately in the given system. The theta B component in the similar manner when applied to the given system with the unit value again will generate the support reaction over here. So, we will again evaluate the value of AM1 and AM2 in the given problem. The values will again be identified with respect to the support reactions which we are getting at this member. So, this is minus of 6 EI upon L square which is corresponding to this member. One must also note that when we are calculating R of B, we are taking the net resultant of the total reaction which is appearing at the joint B, which is the contribution of the member AB as well as member BC of the given system. But when we are calculating the member forces, member force contribution is only defined individual to each member of the given system. So, AM1 contribution will only take into account the first component of the reaction force, whereas when we move to the AM2, in that component this particular part or its equilibrium condition over here will be evaluated. So, this component as a net effective resultant will not be appearing to calculate the AM1 or AM2 component of the given system. With this idea in mind, we realize that AM1 will be minus of 6 EI upon L square and AM2 will be positive of 4 EI upon L in the given system. Similarly, when we move to the AM3 and AM4, the values could be identified as minus of 6 EI upon L square and 2 EI upon L for the given problem. With this idea in mind, we have now got the values of A of RD and value of A of MD, which are the components of the reactions and the member forces with respect to the unit amount of the deformations in the direction of the free degrees of freedom of the given system. Now, once we have these values, we just go back to the same previous step and see that the evaluated values of the AMD and A of RD can be constituted or can be substituted over here. The delta value has already been obtained in the previous step. So, now we have the values corresponding to these expressions known to us. At the same time, we also realize that the member forces will also be getting contributions with respect to the fixed end reactions of the given system. So, even if we are converting our system into the equivalent joint load problem, the fixed end reactions will be generated and those will also be contributing to the end forces or the member forces of the given system. So, with respect to these member force components, also we evaluate the response and we call it as the member load components for the system. In order to know these values of the A of ML, we consider the system with the fixed ended part subjected to the external load, evaluate the system reactions, and in the direction of the same system reactions, we know the values of AM1 with respect to the fixed ended part, AM2 with respect to the fixed ended part, AM3 with respect to the fixed ended part, and AM4 again with respect to the fixed ended part. So, these are the 4 values which have been identified over here. We have written them as a of ML in this case, and these values will appear as WL by 2 positive upward, WL square upon 12 which is negative because it is clockwise, and for the member 2, as there are no member loads available, it will be 0 for both the cases in the given system. Now, with this idea in mind, we realize that the overall net member force can be calculated by contributing the members with respect to A of ML and the member contribution which we have just evaluated with respect to this overall expression in the given system. In the same manner, we can now evaluate the system reactions also. We have evaluated the system reactions over here due to the deformations and their components. Now, we will also add those reactions which are directly active in the direction of the given R1 and R2 as an external load. What does it mean? That when we converted this system into the equivalent joint forces, we identified the system into a scheme like this, where there were some of the forces which were directly appearing at these two joints, which are in the direction of R of A and R of B of the given problem. But in the whole analysis up to now, we have not included these forces anywhere. So, what we do at this step, we consider these forces as A of RL in the given problem, and we add their contribution in the given system at this point. We realize that with the fixed ended system, if we calculate, we can just reverse their direction, and that also becomes the equivalent joint load of the given problem. So, with that idea in mind, I get the value of A of R in the direction of R A, which is W L upon 2, because I will just reverse this value of the load and it will become W L upon 2 as the equivalent joint load over here. With respect to the joint B, the force will again be W L upon 2, because this is the reaction downward upward. So, its component over here will be identified, and that is W L upon 2 for the given system. As I am writing these systems as a reactions, so the value of the load which we are identifying, either I have to reverse its value or I have to just consider the value which are appearing with respect to the fixed ended reaction in this given system. So, this is the second component with respect to R of B, and finally, with respect to R of 3, which is the reaction at the support C, I realize that there is a load of WL directly active here. So, corresponding to that, I will have a direct reaction at that point, and that is R of C component of the given problem. So, with these three components being evaluated, one can now evaluate the effective net resultant value of the system reactions as well. So, as we have got the values of the system reactions, we now move finally to generate all the values corresponding to it. So, we substitute the values of the A of ML, A of RL in the given system, also evaluate these responses of the given system, as these include the multipliers of the system with respect to a 4x4 matrix. So, you may need some of the computational tools like a MATLAB program or a simple mathematical calculator to do these computations, and by doing that we can evaluate the system response for these reactions and the member force components of the given system. Once we have the member force component known to us, we can now also realize that R of C, which has been evaluated over here, is same as the A of M5, which is the reaction in the spring component of the given system. The only difference is that both will be equal and opposite to each other. With this, we stop over here. We have briefly discussed the implementation of the stiffness approach for the similar partially restrained problem. We followed the step in a very systematic manner, but the steps were briefly shown with respect to their numerical values. It is believed that now you can take up the same problem and try these steps one by one on your own and check that whether the values can be obtained in the similar manner. With this, we stop over here. Thank you everyone.